We've already answered A and B on my videos on Mr. Muskluck AP Chemistry FRQ playlist. Let's tackle C and D. There's some special things here because they're both calculations, and you have to be able to do these calculations quickly, roughly 2 minutes each. So I'll give you some tips that will help on that. So on to I. Both of these problems are solvable using some equations, and there's no reason you should get them wrong if you know all the tricks, and also learn how to do them quickly. So let's start with this. Calculate the energy in joules of one photon of violet light with a wavelength of 423 nanometers. In AP Chem, they usually talk about photons of light in terms of nanometers, billionths, 10 to the negative 9 meters. And violet light, right here is 400, 429. I think that's a pretty good description. That's violet. That's the violet that you would get from the potassium flame, where electrons dropping down from an excited state produce that violet. Well, how are we going to calculate energy? Well, equation sheet time. Here's the equation sheet, and at the very top we've got atomic structure, and we've got the equations for energy of photons. And we have energy, frequency, wavelength, Planck's constant, speed of light, and we'll even use the Avogadro number. Every one of these numbers is going to be used. And both of these equations will be used. You should have these memorized, because having to flip forward and write them down and figure out what they are, you're never going to be able to finish the AP exam on time. You're going to be missing so many points because you won't be getting to question number 5 in the first place. So let's go to the question. Calculate the energy of one photon. Well, before you can calculate that energy, you're going to have to find the frequency of that energy, because the equation that finds the energy of a photon is based on frequency. So step 1, let's find the frequency of that light. To do that, you're going to have to take the speed of light and divide it by the wavelength. C divided by lambda, that's what's new. That gives you the frequency. Pull up the calculator. Time to do the calculation. We want to do it quickly. Well, first of all, don't use their speed of light. Who needs the speed of light to 4 significant digits? Never on the AP exam. No, that's 3 times 10 to the 8th meters per second. Divided by, problem here, they give us, and they always will give us, wavelengths in nanometers, and we need it in meters when you're dealing with the speed of light, and that's the only time you need nanometers. So parentheses, 423, and 1 times 10 to the negative 9, and they'll give us a frequency. We know these frequencies are always huge because these are small wavelengths going by us at the speed of light. Yeah, times 10 to the 14. Now, that's the frequency. Let's see if that was right. Here I've got the answer. Yeah, and this is per second. That's what frequency is, or hertz, if you want to give some credit to Heinrich Hertz, who came up with this frequency type stuff and electromagnetic radiation. Now, changing the frequency into energy requires taking Planck's constant and multiplying it times our last answer. So pull the calculator out, times. Don't retype that number in. It's never going to work. You're going to get it wrong. 6.626 times, okay, 10 to this super small number, negative 34. That's a tough one to remember. Those are joule seconds. Multiply that by per second, and you get the photon energy, which is, it's going to be a small number. Let's see if we got it right. With this calculation, 4.7 times 10 to the negative 19. Thank goodness we got that right. Now, there are a lot of risks in taking this. You had to copy these numbers down correctly. You had to have your equation sheet next to you. You have to do this quickly. Now, there's a couple of ways that you can speed things up, and I think they might be worth your time. So let's go over some tricks to make this calculation faster. First one, we're going to take our calculator. 3 times 10 to the 8th, that's pretty easy to remember. That's worth doing. Speed of light, 3 times 10 to the 8th. But Planck's constant is used typically at least once on AP exam, but I don't want to memorize and type out 6.626 times 10 to the negative 34. So with this calculator, store alpha Planck, enter. Now, next time I say alpha Planck, I get Planck's constant. 2 keystrokes saves me 1, 2, 3, and looking it up, and that's worth keeping in your calculator. In fact, if I clear my calculator, clear, and turn it off, and turn it on, that's still in there. It's going to be there until I replace it, the batteries, and maybe if I replace the batteries, it'll still be there. You can always check it. There it is. There's my Planck's constant. There's one other number that's a messy one that you have to put in quite often, and I'm going to do that right now too. It's my favorite. It's one that I remember, but it takes quite a bit of time to type in. 6.022, that's on the equation sheet. There it is, Avogadro's number, 6.02 times 10 to the 23, whatever it is per mole. Second time, E, 23, big number. And of course, typically in chemistry, that is N, the Avogadro number. I wouldn't use A because it's the beginning of the alphabet. And store as alpha N, Avogadro's number. Enter, double check, alpha N. Don't have to type in 6.022 E23. If you want, you could put the speed of light in, but you're not going to save many keystrokes with that. You should know the speed of light anyway. So let's do this problem again. So let's see if we can figure this out easily. I'm going to make it all in one step. The speed of light times Planck's constant, alpha P, divided by 423, divided by 1 times 10 to the negative 9. See if we get the answer. Yeah, there it is. One little step. Notice you don't have to type a times in if you use the letter. If there's a number and then a letter, it knows automatically that you're doing some multiplication. So that can be done pretty quickly, knowing that you're going to have to take the speed of light and divide it by the nanometers to get the frequency and multiply times Planck's constant. You can do it all in one little line. So that gives us our answer. Now let's go on to the next problem. Is the energy of 1 photon of violet light sufficient to cause the ionization of the potassium ion? And justify your answer. Well, what about our potassium ions? Here's their ionization energy. Here's potassium, 4.19 times 10 to the 5. Pretty big number, but this is per mole. This is the ionization energy per mole. Now, we've got photon energy, but just per 1 photon. We need to scale it up per mole. So let's take our answer that we had, the energy of this violet light, 423 nanometers, 4.7 times 10 to the negative 19, just 1, and multiply it times the Avogadro number. That's going to be easy to do. So, calculator, I have my last answer. So, I'm going to multiply that last answer times, guess what? Alpha N, the Avogadro number. Don't have to type it in. It's a big number, 28,000. Oh, what is it? Move that decimal point over. We would need to move it over 5 places. Here's our number, and just move that out into scientific notation and pull my calculator out again. Yeah, there it is. 1, 2, 3, 4, 5, 2.82. And you need 4.19. So, no. Answer the question. Well, first of all, we justified by doing the calculation. And then we said, no, 423 nanometer are not going to have enough with only 2.83 times 10 to the 5 joules per mole. We've got too little to ionize, so that's our answer. So justified our answer, and we gave our answer. 1 point earned for the correct energy and the conclusion. Now let's spend a little bit more time on this because this is an important topic. And here's my outline that talked about photons and what they can do. When a photon hits an electron and it's an X-ray photon, you get ionization. So if you anticipate to ionize something, get yourself a heavy-duty photon, an X-ray, short wavelengths. That's what you've got to know. If you're dealing with ultraviolet and visible light, usually the best that you can do is when you hit one of these electrons with a photon, that kinetic energy is absorbed into potential energy. You can just move the electron up an energy level or so. But the ultraviolet and visible, when you take that kinetic photon energy, it creates more potential energy by lifting the electron away from the nucleus. Now, there's some exceptions to that, but that's generally what you need for AP exam. When you get to infrared, you only get to shake around a few molecules. You get molecular vibration. The molecules wiggle back and forth, and microwaves can only rotate molecules. Those are the types of photon interactions with matter that you're expected to know in AP Chem. So that's worth remembering. I've got that on the study cards, so check that out on the study cards. Here I've got the energy in the photons, and down here I talk about X-rays ionizing, ultraviolet may be able to ionize outer electrons, and here's that diagram. That's worth running. And also we've got the electron orbital filling and such. So in AP07 in our flashcards, worth reviewing.